Hello and welcome back to our video series on anaerobic digestion. Today we are going to learn about the ideal pH range for the operation of anaerobic reactors. pH is a critical operations parameter and all anaerobic reactor operators are highly concerned about it. This is because any disturbance to the delicate balance of the mixed methanogenic cultures lead to slowing down or complete cessation of methanogenic activity. Acidogens, the fastest step in anaerobic reactors, can proceed at the normal rate even under upset conditions, generating volatile fatty acids and carbon dioxide gas. The methanogenic step, which removes acetic acid and carbon dioxide gas and regenerates alkalinity, slows down significantly under such upset conditions, leading to a decrease in reactor alkalinity and eventually a drop in pH. Under extreme conditions, this pH drop can make the reactor sour, leading to a costly reactor restart. Alkalinity is the ability of water to resist pH drop when acidic substances are present. Operators of all anaerobic reactors want to guard against reactor upset conditions due to low pH, and hence pH and alkalinity are extremely important parameters for successful anaerobic reactor performance. So let us begin with understanding pH value. pH is defined as the negative log of hydrogen ion concentration in a given solution. It signifies the balance between the alkaline and the acidic ions present in the water. A pH value of 7 is considered to be neutral since at this pH both hydroxide and hydrogen ions are present in equal concentrations in a solution. It is noteworthy that pH is a logarithmic scale, which means even 0.3 unit decline in the pH value indicates doubling the hydrogen ion concentration, responsible for the acidic nature of the water. On the other hand, increasing the pH by 0.3 units means the water needs twice the amount of hydroxide ion it currently has to increase that pH. As shown in the figure, when the pH value declines below 6, the activity of methanogens typically starts to cease. Moreover, if the pH increases beyond 8.5, a sharp decline in the methanogenic activity is observed. Most anaerobic reactors operate successfully between pH values of 6.5 and 7.5. pH values also determine the toxicity of compounds such as volatile fatty acids, hydrogen sulfide, and ammonia, since pH values dictate the transport of chemicals in and out of the microbial cells. As shown in the adjoining figure, the sulfide ion has a pKa value of 6.9 at 37 degrees Celsius, which means at lower pH values, a larger fraction of the sulfide is present as hydrogen sulfide, the protonated and toxic form of sulfur. On the other hand, an increase in pH leads to an unprotonated form of ammonia, which is more toxic form of ammonia. Hence, changes in pH beyond the ideal range can make these commonly present compounds more toxic to methanogenic cultures. This makes pH a key parameter when substrates with high sulfur and/or ammonia are being anaerobically digested. Processes that are anaerobically digesting proteins can have both higher sulfur and ammonia simultaneously. Moreover, industries such as pulp and paper processing wastewater are known to have higher quantities of sulfur in wastewaters. In such processes, understanding the ideal pH ranges for successful methanogenesis is of vital importance for successful operations. Alkalinity is the ability of water to resist a drop in pH. CO2 bicarbonate alkalinity dominates as the main form of alkalinity in anaerobic reactors because typically biogas contains a significant amount of highly soluble carbon dioxide gas. Moreover, the generation of sulfides and ammonia during the anaerobic digestion process contributes to the metabolism generated alkalinity during the anaerobic digestion process. Under anaerobic environment, alkalinity is consumed in neutralizing the volatile fatty acids and carbonic acids generated during the anaerobic digestion process. Once the volatile fatty acids are consumed by methanogens, the supplied alkalinity is regenerated in the reactor effluent. If an anaerobic reactor has sufficient hydraulic retention time, a portion of this regenerated alkalinity can be recovered by recycling a fraction of the effluent back to the front end of the anaerobic reactor. Now let us discuss how to calculate the alkalinity demand for a process. If the reactor head space carbon dioxide concentration and the reactor liquid pH are known, bicarbonate alkalinity can be calculated by combining the universal gas law, Henry's gas-liquid partitioning coefficient law, and Henderson-Hasselbalch equation. After the combination, the derived equation obtained is shown here. The equation can be used for estimating bicarbonate alkalinity in the anaerobic reactor. If the existing alkalinity in the reactor influent water and the concentration of volatile fatty acids are known, this equation can be used for calculating the additional alkalinity demand, if any required, to maintain the reactor in an ideal operational pH range. The latest trend in high-rate anaerobic reactors is to build taller reactors due to their superior loading rates and smaller footprints. This can lead to an increase in the solubility of carbon dioxide in the liquid due to higher pressure, and hence such processes may demand additional alkalinity if naturally present alkalinity is insufficient to meet the demand. In unbuffered waters, a depth of 10.33 meters can decrease the pH by a 0.3 unit change due to higher CO2 solubility. We just learned how dissolved carbon dioxide plays a crucial role in total alkalinity demand of an anaerobic reactor. This also means that online pH probes are critical instruments for the operation of high-rate anaerobic reactors. Since during the sampling process, some CO2 is bound to be vented, increasing the pH and alkalinity of the sample taken. Moreover, whenever a sample is taken to measure alkalinity and pH, the same container must be completely filled with the reactor fluid, and it must be capped immediately to avoid potential CO2 escape. You'll also notice that the pH of an anaerobic reactor sample kept on a bench exposed to atmospheric pressure will gradually increase due to the escape of carbon dioxide gas. I hope this video gave you a thorough understanding of reactor pH and alkalinity demand. We'll continue our discussion about volatile fatty acids and alkalinity in another video. If you have any further questions on this subject, please feel free to contact our anaerobic digestion experts at the contact details given below. Thank you so much for your time and attention, and I look forward to seeing you in the next lecture of this video series. Bye.